You are familiar with electrons as small negatively charged particles, but electrons can also behave as waves. This is called wave-particle duality. Light can also behave as particles called photons, and as waves. What is wave-particle duality? To understand this, we need to state some evidence for the particle-like behavior of electrons. Describe how the wave-like behavior of electrons can be demonstrated using a double-slit experiment. Calculate the de Broglie wavelength of a particle and explain how the diffraction pattern of a stream of electrons depends on the wavelength. You are used to the idea of electrons behaving as particles, with mass and charge. These particles behave as you would expect. They can be deflected by an electric field and hit the screen with discrete impacts. When a stream of particles is fired at two closely spaced slits, each particle will either go through one slit or the other. Two bands are formed on the screen. When a wave travels through two slits about a wavelength wide, each slit behaves like a source of waves. Waves from the two slits are superposed and interference occurs. We see a different pattern and graph depending on whether particles or waves have travelled through the slits. So, what happens when a beam of electrons is fired at two slits? You might expect each electron to pass through one slit or the other, and so produce two bright bands on the screen. However, when physicists do the experiment, what they actually see is an interference pattern, just like the one that we see with waves. Physicists were surprised by the results and thought that maybe the electrons were bouncing off one another. They tried firing the electrons one by one, but still saw an interference pattern. The electrons seem to behave as particles when they leave the gun and arrive at the screen, but as waves when they pass through the slits. When electrons behave as waves, their wavelength is called the de Broglie wavelength. This is equal to Planck's constant divided by the momentum of the electron. For an electron travelling at 1/5 the speed of light, the de Broglie wavelength is 1.2 times 10 to the minus 11 meters. To see a diffraction pattern for a beam of these electrons, you would have to pass the electrons through gaps on the order of 10 to the minus 11 meters wide. Where can you find gaps this size? The answer is in the atomic spacing of crystals, such as the spacing between the carbon atoms in polycrystalline graphite. A diffraction pattern is formed when a beam of electrons is fired through a thin slice of polycrystalline graphite towards a fluorescent screen. The pattern is a ring instead of a series of bands because the crystal gives a whole set of gaps for the electrons to travel through rather than just two slits. The electron gun uses a potential difference to accelerate the electrons. Increasing the potential difference causes the electrons in the beam to travel faster. The higher momentum of the electrons corresponds to a shorter de Broglie wavelength, and so the electrons are diffracted less and the rings in the diffraction pattern are closer together. Electrons sometimes behave as particles and sometimes behave as waves. An experiment in which electrons are diffracted by polycrystalline graphite provides evidence for the wave-like behavior of electrons. The atomic spacing in graphite is similar to the wavelength of the electrons, the de Broglie wavelength. Increasing the speed, and therefore the momentum of the electrons, decreases the wavelength, reduces the amount of diffraction, and results in a diffraction pattern with more closely spaced rings.